Welcome to Query Processing. In this unit, we'll talk about query transformation rules. Let's look at a query. This is an average query we might encounter, and this is our example query. We're going to select the employee name, and we're going to create a join between or among three tables, the employee, the assignment, and project table. And we're only going to be looking for titles that are programmer. So those are employee titles that are programmer, where projects are greater than 100,000 and the duration of a project is less than 12 months. Very, very reasonable query. The first thing we do is create a tree in the order of projections, selections, and joins. So we take that relational algebra expression and now create a query tree as a result. So we move the projections to the top and we say that we're going to be projecting ename from the result of it all. And the next things we're going to be doing actually from the top of the tree is selecting the title programmer, duration less than 12, and budget greater than 100,000. And that's going to be operating on a join between the project table and the result of a join between the assignment and the employee table. So looking at this as a query plan that we would pass to a query execution module, it would look at this tree from the bottom up and determine what it needs to do based on the structure of the tree. In essence, these are instructions sent to a query processor. So not only is this a representation of the query of the relational algebra query, but it's a representation of the instructions sent to a query execution module. So the first thing the query execution module is going to do is it's going to join the assignment table with the employee table. And because it's at the bottom of the tree, and it's going to be joined on the employee number. The results of that are now going to be sent to another execution module piece where it's going to join that result with the project result, the project table, and then it's going to take that result and apply a selection of budget greater than 100,000. And it's going to take its result and select only those that have a duration of less than 12, and take that result and apply another filter, title equals programmer. And finally, it's going to project only the employee name column. So we have a sense that this query plan, in essence, will take a certain amount of time to execute. So we'd like to apply some heuristics to query tree in order to derive a semantically equivalent query tree, but something that would be fed to a query execution planner that would be that would actually operate much quicker and evaluate much quicker. So there are a number of rules that we can apply to do the manipulation of this tree. These are some of the tree transformation rules. And in my discussion here, we'll assume that R and T are two tables, and they both consist of attributes 1, 2, 3, all the way through N. These are columns of the table. And we have a separate table called S, and it has also attributes B1, B2, B3, all the way to Bn. So for tree transformation, we are going to look at, number one, the commutative law. We'll see that an R cross S, cross product between R and S, is the same as a cross product between S and R. And a join between R and S is the same as a join between S and R. We're thinking, of course, that's true. But these two expressions mean very different things to a query processor. As we'll see through this module and the next module, that the way the query processor will evaluate these is very different based on the order of the operation. R cross R join S, for example, makes R the outer table and S the inner table. S join R makes S the outer table and R the inner table. And why is this important? Suppose that table S has an index on it and table R does not. So we saw from the last video in this module that if R is considered the external table, we read one row of R at a time, and for each row we read of R, we find the corresponding row of S. How this is done, since S is indexed, by looking at a B plus tree that represents the index of S, which is a log n operation, which allows us a log n read to find the corresponding rows in table S. Contrast that with the other expression, S join R, where S has an index on it, but R does not. If S is going to be considered the outer table, and it will because the query processor doesn't know any better, it'll start reading a row of S one at a time. It'll look for the corresponding row in R, except R is not indexed. Essentially, that's going to be We're going to, for each row in S, we're going to have to read a corresponding all the rows of R. And for each subsequent row of S, we're going to have to read all the rows of R again. So whereas the left-hand expression, the left-hand side of the equal sign, it's an n log n operation. On the right-hand side of the equal sign, it's an n squared operation. So, but we know that these are semantically equivalent to each other, and a good query optimizer will look at the various options, understand which of the tables are indexed and which are not, and potentially reverse the order of the join. Won't change the meaning of the join, but it will certainly change the way the query processor approaches joining S and R or R and S together. Provide a better choice for a more optimal query. Similarly, we have the associative law. So R cross S, taking its product cross T, is the same as R cross the product of S cross T. And the same thing is true for natural joins. And again, depending on the index structure, one may be more optimal than the other to execute. There are transformation rules for unary operators. So if you're doing projects and you have a set of attributes A, and A prime is some subset of the attributes, and A double prime is some subset of the attributes, and A prime is even a subset of A double prime. So if we have a projective A prime and A double prime on R, it's equivalent to saying projective A prime. We can get rid of the whole layer of projections by applying this transformation rule. Similarly, if we have two sets of selections on one table, instead of representing them as two selections, we can transform them to be an and of the two selection criteria on that table. Much faster operation. We have commuting selection with projection. So if we're projecting columns A1 through AN after selecting some based on some predicate of table R, we can actually pull out this, so we can actually push the projections in to table R. So we're actually dealing with a much smaller set of data, meaning only the columns we're interested in on table R plus the column A sub P, and provide all the selections on A sub P on a much smaller table, and then ultimately project out A sub P if we don't need A sub P. If A sub P is one of the A1 through ANs, then it's not a separate attribute, and then we don't even need the outer projection. And what the transformation from the projections on a selection relation just become a selection of projections on a relation. It could be much faster. Another transformation is if a selection applies only to one table. So if we say selection of R cross S versus selection of maybe that selection criteria only applies to R, we can move that selection in to only deal with table R, and then we apply, then the result of that is a much smaller result, and then that means that the cross product of the smaller result and S is much more efficient to calculate than the cross product, and then applying the projection. Similarly, it's true for natural joins. We could apply the selection criteria much earlier, but we could push it down to the table that's appropriate, and then take its product, take its result, which is going to be much smaller than the entire table, and join it with table S. We look at R union T, when you have a selection criteria applied to the union operator. If that selection criteria only applies, it'll apply to both because we're doing unioning. We can take that projection criteria, move it down to both tables, minimizing the set of rows that we have to deal with before we do the union, and it can make the union a much more efficient operation. The next transformation rule is commuting projection with binary operators. So if C is a set of attributes, I have attribute A prime and B prime. A applies to table R, and the B's apply to table S. So if we project C from R cross S, that's really taking, and C is the union of A prime and B prime, we can take the A primes that are associated with R and just project those columns from R, from A prime, and then cross product them with just the columns that we need from S, and columns B prime from S. Similarly, we can apply this to a natural join, where if we have projections of certain columns, instead of creating the whole natural join first and then applying the projection, we can push the projections down to the bottom level, and then now form the projections of join on the products of the projected rows of each table. Now, applying this to a query tree. So what we want to do to our original query tree is take all the selection and projection operators that we saw in the rules, especially rules 4, 6, and 5, and push all projections down as far as we can and push the selects down as far as we can. So pushing the selects down as far as we can, we notice project greater than 1,000 applies to project, duration less than 12 applies to the assignment table, and title equals programmer applies to the employee table. We take the result of that and apply it to the projection. We notice that the projection on the project table is we just project out P number, and the product of P number and E number is we apply the project of P number and E number to the result of applying the selection to the assignment table. And then finally, we project only the columns that we need from the employee table. We join the results of the assignment table and the employee table, but just only the columns and the rows that we need. And we now produce the resulting table, and we project out of that just the project number and the E name. And then we take the results of that and join that to the product of the results of the project table. We perform a natural join on that and now perform a project on eName. Now let's do this with horizontal fragmentation. Now assume that the employee table is fragmented into 3 different fragments. We have employee 1, employee 2, and employee 3. If the query predicate is choosing employee number less than E4, then employee 3 is excluded from the join. So any table that's defined based on a predicate, we see the predicates defining fragment 1, 2 are not contradictory to the query predicate. Enum is less than E4, but the predicate defining fragment 3 is contradictory to that query predicate. We can eliminate it from our query plan. So if we look at the select reduction, we normally would be unioning 3 fragments to produce a result, and then we'd apply a selection criteria of enum is less than E4. But if we notice that that selection criteria is only applicable to employee fragment 1 and employee fragment 2, we can eliminate employee fragment 3 from the table, from the join expression. Similarly, we can apply this to a join reduction. If we're joining different fragments of R and different fragments of S, we can just pick the fragments that have the same or reasonable connection between their fragment definitions. So moving on to the next slide, if the union of 3 fragments of employee is joined with the union of 2 fragments of the assignment table, and the assignment 1 fragment, the predicates that define the rows of the assignment 1 fragment will overlap with the predicates that define the rows in the employee 1 and employee 2 fragments overlap, and then predicates that apply to the assignment 2 table and the employee 3 table overlap, we can rewrite this whole join plan and just join fragments employee 1 and assignment 1, employee 2 and assignment 2, and finally employee 3 and the assignment 2 fragments. We join those results and union them together. Vertical fragmentation reduction is the same way. If our query is only asking for certain columns and some fragments do not contain that column, we can eliminate it from the definition of the query from the query tree itself. So if we're joining fragments employee 1 and employee 2, and then we only want to project the employee name, so in reality we can ignore the join because the employee 1 fragment is the only fragment that has the projective ename. So therefore, our new query tree becomes a projective ename on the employee 1 fragment.